We tackle a lot of the very serious problems of the world through the application of our science and technology. And of critical importance to our science and technology is that the underlying mathematics, the thing that props it up, is logically correct, whatever that means. And at the heart of whether or not mathematics is correct is this little question of whether or not 0.9 recurring can be said to be equal to 1. It can't be stressed enough how important this little question really is. Many people don't believe that 0.9 recurring can be said to be equal to 1. But there are many different opinions about why it can't equal 1. And so people that disagree with the statement often disagree among themselves about the reasons why the equivalence is wrong. Also, many people agree with the main mathematics community that 0.9 recurring does equal 1. But even the mathematicians disagree among themselves about which proofs are valid and which proofs are not. In this video, we're going to focus on one particular disbeliever's view, which just happens to be my view. And on the opposing side, we'll also consider a typical collection of mathematicians' views. We are going to show that if we have a fundamentally different approach to mathematics, then we can produce a pretty good argument against any proof that 0.9 recurring equals 1. And this different approach to mathematics is that all definitions or axioms and all rules of logic must be valid, where being valid means it can be explained by reference to things in the real world. We will explain why the concept of limits is highly problematic, and critically, we will explain why this different approach to mathematics is incompatible with the existing mainstream approach to mathematics. Only one of them can be correct. They can't coexist as different mathematical systems. And this approach of an incompatible version of mathematics stirs up a lot of hatred from certain mathematicians, who think that if anyone questions the validity of the foundations of their version of mathematics, then they must be wrong, because they know that they are right. And so you need to be warned that this non-standard approach is detested by the wider mathematics community, who believe that young minds should not even be exposed to these arguments for fear of being corrupted. Most mathematicians are happy for you to have your own non-standard system of axioms in which 0.9 recurring doesn't equal 1. They might even be happy for you to claim that 0.9 recurring is not well defined in your particular system because you only allow finite objects. But they will blow their top if you question the validity of it in their mainstream mathematical model, or if you question their foundational principles, which seem to be a taboo subject in that nobody is allowed to question them. They get so annoyed that reason appears to go out of the window, so instead of getting a reasonable answer, you're more likely to get ridiculed or even censored. At best, your opinions will simply be dismissed, because, you'll be told, superior minds must have already resolved any issues that your feeble mind might come up with. And you can guarantee that they'll tell you that you simply don't know what you're talking about. If we accept the standard approach used by the mathematics community, then it is difficult but not impossible to argue against 0.9 recurring equals 1. And later we'll do just that, using a cat and mouse argument. And if we reject their particular axiomatic approach, and instead we claim that we need a fundamentally different approach to mathematics, then in our approach we can claim that 0.9 recurring can't equal 1. If we take a step back and look at the bigger picture, this situation is very similar to the different approaches explaining the current state of life on Earth. Creationism was the widely accepted approach when the theory of evolution came along. and the creationists wanted to ban the evidence-based approach from being taught in schools for fear of corrupting young minds. Do we really want to banish alternative viewpoints like the creationists wanted to? Or should we allow the merits or otherwise of alternative viewpoints to be assessed through honest and open debate? Even if the scientists were unable to come up with evolution or any alternative theory to creationism, they should still object to the creationists' approach, because they should insist that for any explanation to be called scientific, it needs to be backed up by empirical evidence. That's what science is all about. I mentioned some of the views presented in this video in a very polite comment on a popular maths forum, whereupon my comment was deleted and I was given a lifetime ban from the forum. The reason given for the ban was crankery, the worst trait of which is that a crank will not engage in intelligent discourse on the basis that they know they are right. Ironically, this is exactly what the moderators are guilty of by banning anyone with an opposing viewpoint. The moderators were also concerned that my comment might corrupt the minds of young students who don't know any better. Here you can see the similarity to the creationists. And if you are going to argue, like me, that 0.9 recurring can't equal 1, then you can expect this type of reception. And so you've been forewarned, your minds might get corrupted. And so watch the rest of this video at your peril. People have been arguing for centuries that 0.9 recurring can't equal 1, with simple arguments like it can never reach 1, or how can 0 point something be equal to 1 point something? But arguments like these are never going to be taken seriously by mathematicians. We need to unravel the mathematicians' arguments and then state clearly what we object to and why. Mathematicians will tell us that if we accept 0.9 recurring is a real number, then we have to accept that it does equal 1. But we don't accept that 0.9 recurring is a real number because we don't even accept the concept of real numbers themselves. This symbol 0.9 recurring was around for over 200 years before it was defined to represent the limit of its partial sums. So it isn't set in stone that it represents a limit, because it hasn't always done that. Not only has the symbol had different meanings in the past, but even today it has multiple meanings because it can be interpreted as a geometric series. And so the symbol is not exclusively reserved to represent a limit. It's not as far-fetched as it might first appear to reject the concept of real numbers. Even a small number of mathematicians reject them, most notably of which is a retired mathematics professor, Norman Wildberger. Norman Wildberger claims that real numbers are at the core of most foundational problems in mathematics, and that objects such as the square root of 2 and infinite sets don't exist. He says we need to rethink a lot of mathematics and expel infinity, and that 0.9 recurring equals 1 should be taken with a large grain of salt. Even so, the supporters of real numbers can get quite annoyed when people argue that 0.9 recurring can't equal 1. They have no doubt that 0.9 recurring is a real number, and that real numbers are valid, and that we can use arguments based on definitions to show why it does equal 1. Or they'll say that we can use a whole bunch of proofs, both formal and informal. But our reply to them is that we can contest all these claims by objecting to the modern definition of real numbers as limits. By the way, please feel free to use a link to this video to start discussions on internet forums and other social media platforms. You might like to start a poll to see which side of the argument comes out on top, because that can be quite interesting. But now back to the main argument. And this timeline shows a period of over 200 years where unending decimals were not defined as limits. And if we take 0.9 recurring to represent the unending series 9/10ths plus 9/100ths and so on, then we can call it an old timer, because unending series have been around for thousands of years, long before the new kid on the block called real numbers as limits came along. Perhaps the main issue with the limit approach is the question of whether or not it makes sense to define the sum of an unending series of non-zero terms to be equal to a constant value. This idea that unending non-zero terms can somehow equal a constant is often justified by the concept of converging to or tending towards. And this is the idea that a sequence can be approaching a fixed value, and this can be a very convincing argument. We might think of the series in terms of a number of jumps, where each term in the series is produced by a looping algorithm that tells us to jump 9/10ths of the remaining distance to 1, and then it goes back to the start of the algorithm. So the first jump needs to get us 9/10ths of the way from 0 to 1. The next jump only gets us a further 9/100ths, and the third jump advances us by the tiny distance of 9,000ths. Clearly, we appear to be approaching the value 1, but we need to distinguish between different types of approaching. There is a type of approaching where you will eventually reach your destination, and there's a type of approaching where you won't, and this is the latter. We could also think of this series as describing a discrete form of deceleration, where the velocity changes from 9/10ths of a unit of distance per unit of time to 9/100ths of a unit of distance per unit of time, and so on. And if things like acceleration and deceleration really do involve a series of discrete velocity changes rather than being a continuous change, then perhaps our whole approach to calculus has been wrong. Now let's consider a different series, 1 plus 1 plus 1 and so on. The first jump takes us to exactly position 1. The next jump takes us to position 2. The third jump takes us to position 3 and so on. This is clearly not approaching a fixed value. We can now perform addition on these series. So we add the first term of the first series to the first term of the second series, and we get 19/10. So our first jump covers a distance of 1.9 units. When we add the second terms, we get 109/100. So our next jump is a little over 1 unit. Next, we add the third terms, and we get 1009/1000. And the series of jumps continues. But no jump will ever be exactly 1 unit, and no jump will land exactly on a whole number. And so here we combined 0.9 recurring with another series to try to demonstrate that there is no constant that it is converging to. But a lot of people won't be convinced by this argument, and so let's try another argument concerning so-called irrational values. Consider a right-angled triangle with 2 equal sides of x pixels. The long side, or hypotenuse, should measure the square root of 2x squared pixels, according to the Pythagorean theorem. But this can't happen, because any line on any screen will consist of a whole number of pixels. And so we can't actually draw a line that is exactly the square root of 2 of any unit of measurement. All we can do is draw a line that is close to some value in the sequence of values generated by a square root of 2 algorithm. Such an algorithm can't complete. It can't do an infinite amount of work and say, there you go, I've produced a constant that is the square root of 2. Unlike 0.9 recurring, there is no constant that we can say the sequence is approaching. So the supporters of real numbers have to dubiously claim that they can imagine a final constant, and since they think they can imagine it, such a point must therefore exist. And so, as I mentioned earlier with the example of Norman Wildberger, even some mathematicians now finally concede that the square root of 2 does not exist. If the sequence corresponding to an irrational number has a constant value which we call a limit, then the decimal representation of that number must contain an actual infinity of digits. And surely any actual infinity is absurd. How can there be no last non-zero term, and yet the sum of the terms is somehow a static value? It doesn't make any sense. The 0.9 recurring equals 1 debate won't go away while blatant absurdities like this one remain unresolved. This problem was even debated by the ancient Greeks. It was about 500 years BC when the ancient Greeks proved that the square root of 2 could not be expressed as a rational value. We are not sure who devised that proof, but it is usually attributed to Hipparchus of Metapontum. Hipparchus was a Pythagorean philosopher. The argument involved line segments and was referred to as incommensurability. The proof could have been interpreted as evidence that such lengths can't exist, especially because the Pythagoreans wanted to believe that everything could be expressed in terms of rational values. But it seemed more reasonable to them to accept the existence of irrational lengths, and that this amazing information was previously only known by the gods. Another prominent Greek philosopher to talk about unending series was Zeno of Elea. Zeno's starting position was that motion is continuous, and his objective was to show that motion is an illusion. So he devised several paradoxes to show that continuous motion leads to absurdity, and many of his paradoxes involved unending series. For example, his most famous paradox is a reworking of the even older fable of the hare and the tortoise. It is a race between Achilles and a tortoise, where the tortoise is given a head start. By the time Achilles reaches the point where the tortoise started from, the tortoise will have moved on. So Achilles then needs to reach the new position where the tortoise has moved to. Every time Achilles reaches where the tortoise was, it will have moved on to a new position. This could go on indefinitely, and so it appears Achilles would need to complete an infinite number of tasks if he is ever going to catch up with the tortoise. And surely it's impossible to complete an infinite number of tasks, isn't it? Next up, we have the Greek philosopher Democritus. Zeno's argument was that motion must be an illusion because it leads to absurdity. And Democritus agreed that motion would lead to absurdity if it was actually continuous. But Zeno's paradoxes could easily be solved if motion was not continuous. And since the concept of continuous leads to absurdity, Democritus concluded that nothing could be continuous, and everything must consist of a finite number of indivisible parts, which the ancient Greeks called atoms. And so this belief was called atomism. If the atomists were right, then everything must consist of smallest parts, including anything real or imagined. And that would include any geometric construction, such as a line segment supposedly measuring exactly the square root of 2. But fiercely opposed to the atomist viewpoint was the rich and influential philosopher Plato. Plato's alternative was a realm of perfect forms, distinct from the real world in which we all live. His theory of forms became known as Platonism, and he founded a large academy which became the birth of all academia, through which Platonism has thrived and atomism has mostly been disregarded. If we accept that a length of exactly the square root of 2 can exist, then it follows that 9/10 plus 9/100 and so on should also correspond to a static fixed length. In which case a journey from A to B should be able to be considered as being a completed infinity of smaller journeys. So when we get past point B, we will literally have gone to infinity and beyond. But just because we know it's certainly possible to move from point A to point B, it doesn't mean that the concept of a completed infinity is the right way to model that journey. The argument that it appears to be successful can't be considered to be a valid argument for using infinity in mathematics. You might expect mathematicians would know better than to use this invalid argument, but they still do. The supporters of real numbers will object to our arguments. They'll say we're not allowed to go back through history to choose a previous meaning, because nowadays, when we write down 0.9 recurring, it means a modern day real number. And they'll say that we've not found an inconsistency. We have merely shown that we don't understand infinity. They are not going to accept our other arguments either, not least because they know that since the value of a real number is defined as the limit of the partial sums, then it's practically defined to be equal to 1. So they'll claim we don't even need the proofs at this stage. A real number is defined as the limit of the increasing partial sums. And for a geometric series, the limit or sum is supposedly well defined. A geometric series is a series with a first term A and a common ratio R, where R is what you need to multiply the first term by to get the second term. And so for 0.9 recurring, A is 9/10 and R is 1/10. We can form an expression for the sum to the nth term that simplifies to k minus k times r to the power n, where k is A divided by 1 minus r. We could describe k as the constant part of the expression, and minus k times r to the power n as being the variable part of the expression, because this will vary as the value of n varies. So, for a so-called absolutely convergent series, the constant part a over 1 minus r is called the limit. And in complete disregard of the obvious fact that it is impossible to add up infinitely many non-zero terms, the sum is defined to be equal to the limit. If the expression a over 1 minus r was really the sum of infinitely many terms in a geometric series, then 1 plus 2 plus 4 plus 8 and so on would sum to minus 1. And minus 1, minus 2, minus 4, minus 8 and so on would sum to plus 1. But supporters of real numbers wanted to claim that the expression could be said to equal the infinite sum in some cases, and so they used definitions, notably convergent and divergent, to exclude the cases that appear to lead to absurdity. If you're not a mathematician, then you might be surprised to hear that definitions or axioms don't need to be valid, because they are deemed to be true by definition. And so if I want to prove that my chair can fly, I could declare that, by definition, all men can fly. And also by definition, my chair is a man. It then follows that my chair can fly. Obviously here, I have defined my way to the answer that I want to achieve. So my argument here relies far more on the definitions that I used, more than the deductive reasoning at the end. The deductive reasoning is fairly superfluous because we can't argue, apparently, with something that is assumed to be true by definition. In the same way, proofs that rely on the formula for the sum of a geometric series are more or less proof by definition rather than proof through deductive reasoning. Another definition-heavy approach concerns something called the equivalence relationship. If a friend asked you to swap a green apple for a red apple, then you might agree, because for many people it seems reasonable to call these two items equivalent on the basis of what is defined as an apple. But what about two endless series? What would be a fair basis of equivalence between these two things? If you think they can be said to represent a constant value, then perhaps it is fair to describe them to be equal on the basis that they have the same constant part of the nth sum expression when they are both absolutely convergent series. But if you think of them in terms of a number of journeys, then you wouldn't swap a ticket that gets you into a show for one that gets you as close as you like to the door of the venue, but no further. It would not seem fair to call these two tickets equal just because they both relate to the same show. But perhaps you would swap, because fairness doesn't matter at all. You would swap because you agree that the same show can be used as the basis of equivalence, and therefore, for you, these two tickets are equal, and the definitions that you have accepted can be used to prove that they are equal. And so if you encounter a clever sounding argument that relies on the expression for the sum of a geometric series, bear in mind that it is little more than a proof by definition. But the supporters of real numbers will insist that their definition approach is completely legitimate. And they will insist that we can't argue against the sheer volume, the vast amount of rigorous proofs. First, we have what's called the intuitive explanation, in which the partial sums are placed on the number line one by one, and we consider what distance remains to the point corresponding to the value 1. Generalizing, the distance from the nth term to the point 1 will be 1 over 10 to the power n. So if 0.9 recurring was less than 1, we should be able to find a point that is between 1 over 10 to the power n and the point 1 for all possible values of n. And since no such point exists, the mathematicians conclude that it must equal 1. In other words, they are saying that 0.9 recurring must equal 1 because if you give me any point before 1, then I can find an nth sum that is closer to 1 than your point. But here we can use a cat and mouse argument, in which we can easily switch the roles of cat and mouse around by saying, you give me any nth sum and I can give you a point that's closer to 1 than your nth sum. And since this will work for all possible nth sums, points must exist between 0.9 recurring and 1. So these are two equal and opposite arguments. One implies there can't be any points between them, and the other implies there must be points between them. You might think this shows that 0.9 recurring cannot be any fixed value, and if it can't be a constant value, then possibly the most obvious conclusion is that it must be process related. But they, the mathematicians, want to justify their preconceived notion of so-called real numbers, in which a real number has a fixed place on the so-called number line. So they choose to only accept arguments that fit with what they want to be true. Here, they want the first argument to be valid and the second argument to be invalid. It doesn't matter a jot that these are exactly the same argument, just switched around. It doesn't matter to them that they are adopting an inconsistent approach to logical reasoning. The only thing that matters is that they can claim that their concept of real numbers is consistent. And if it can be made consistent by rejecting the second argument, then so be it. To a disbeliever, like me, this can't be a valid approach, because any ridiculous notion can be called consistent if we are allowed to reject any argument that shows it to be inconsistent. If we're going to be consistent in our approach to logical reasoning, then we must deduce that 0.9 recurring cannot be a constant. But the supporters of real numbers just won't let go of the idea that it is a constant because they've defined it to be a constant. Yes, it leads to contradiction when we assume it is less than 1, but it also leads to contradiction when we assume it equals 1. It's the same kind of logical argument except turned around. But they don't care about the second contradiction. They don't want to talk about it. They won't even acknowledge that the second contradiction exists, because if they did, then they'd have to acknowledge that there's a problem with real numbers. The ignored contradiction is just one of the problems with the mainstream's intuitive explanation. Another problem is that it involves infinitely small points on an infinitely divisible, infinitely thin number line that goes from minus infinity to plus infinity. We can imagine a thick line, but when we try to imagine an infinitely thin line, it completely disappears. Nobody can truly imagine infinitely small points and infinitely thin lines. We can only imagine solid lines and solid dots and pretend that these represent infinitely thin lines and infinitely small dots. And so the belief that it is valid to theorize about such things has to be based on pure faith. And for those of us without this faith, that we can imagine infinitely big things and infinitely small things, it is invalid and absurd to think that we can conceive of and theorize about such objects. And a third major problem is the problem of the last term. Given that all the points in the sequence 0.9, 0.99 and so on are supposedly static points on the number line, then how can there not be a last point? If we approach the number line from the right, then which of these static points will we encounter first? Or, if we think of these points in an ordered infinite set, and we add a number that's bigger than 1 in this set, what number will immediately precede it? We can't just avoid the issue by saying the least upper bound is 1, because 1 is not in the set. Or, if we approach 1 from the left, then how can we have passed an infinite amount of these points when we reach the point 1? And how can we not have passed a last point? We've already seen that we can't construct a length of the square root of 2, because we can't have an irrational amount of pixels on a screen. But do irrational values actually exist? Do values like the square root of 2 really exist on a ruler? If we move our finger along a ruler, then have we really just travelled past all the points? 1, 1.4 and all the other points in the base 10 representation of the square root of 2? Surely we can't suddenly change from having passed a finite amount of these points to having passed an infinite amount of these points, can we? And if we can't transition easily from finite amount to infinite amount, then we've got a clear absurdity here. And the only way that we can avoid this absurdity is to conclude that irrational lengths can't exist in the real world, and that space itself must consist of a finite amount of smallest parts. But the supporters of real numbers just dismiss all these problems, and they restate their intuitive argument as a formal proof that has been accepted by the mathematics community at large, and so they'll claim it can't be argued with. For them, it is an undeniable proof of equality. The formal proof starts by assuming that 0.9 recurring and 1 are both constant values, and then, if they are not the same value, then there must be a value between them, which we'll call x. But as disbelievers with the arguments we've made earlier, we've already established that 0.9 recurring can't be a constant value, and so by rights we should be working with series, not with fixed values. And so our version of their argument is that if 0.9 recurring and 1 have different series, then a series can fit between them, which we'll call x ... In the formal proof, they consider the sum to the nth term, and they claim that all nth sums are less than 0.9 recurring in its entirety. Whereas working with series, we can say that the nth sum of x ... should be between the nth sums of 0.9 recurring and 1. In the formal proof, they use the fact that the sum to the nth term is a distance of 1 over 10 to the power n away from 1 to deduce that 1 minus x must be between 0 and 1 over 10 to the power n. But if we use the same fact when working with series, we can deduce that 1 minus the nth sum of the x series must be between 0 and 1 over 10 to the power n. In the formal proof, the muddled logic continues with the idea that 1 over 10 to the power n can be replaced by 0. Therefore, 1 minus x must be less than or equal to 0, thus proving that any value we try to place between them must equal 1. Therefore, they must be the same value. Whereas with the series approach, we can find as many series as we like between 0.9 recurring and 1, such as 95 over 100 plus 45 over 1000 plus 45 over 10,000 and so on, which happens to be exactly halfway between 0.9 recurring and 1. But they will insist that their proof is still valid, because a proof is deemed to be valid regardless of whether or not the premises or assumptions are valid. Just try to get your head around this. It doesn't matter if we wrongly assume that 0.9 recurring is a constant, because the proof that it must equal the constant 1 will still be valid regardless. Perhaps the simplest of all the proofs is the convincing argument that we all encounter at an early age. We are taught that the division process of 1 divided by 3 will yield an infinite result. And it feels right that 0.3 recurring must equal a constant, because we presume that any whole cake can be divided into 3 equal parts. Then 3 times this infinite answer, which is 0.9 recurring, must equal a whole one, just like 3/3 of a cake equal a whole one cake. But does the division process really produce an infinite result? After getting the first 3, there's a remainder of 1/10 that still needs to be divided by 3, meaning there's a remainder of 1/30. After getting the second 3, there's a remainder of 1/300. After the third 3, there's a remainder of 1/3000, and so on. And in general, after processing n decimal places, there is a remainder of 1 over 3 times 10 to the power n. So there will always be a non-zero remainder. The remainder can't go away. But if we want to believe in infinity, then we can easily be persuaded that an actual infinity of decimal places is theoretically possible, and our imagination can convince us that the remainder must disappear. But if we reject these arguments as fantasies, then we might come to the conclusion that 1/3 can't be fully represented in base 10, and that not all cakes can be divided into exactly 3 equal parts. Even though the wider mathematical community concede that we can't actually perform an infinite division, they believe we can still theorise about what the result might be if such a thing could be done. But if we are to believe that we can imagine something as strange as a completed infinite process, then we might as well imagine that we could end up with an infinitesimal, which is equally as unbelievable. And if we end up with an infinitesimal, whatever that is, then 0.3 recurring would not equal 1/3, as it would be an infinitesimal distance away from 1/3. I know this sounds ridiculous, but everything sounds ridiculous where infinity is concerned. And since nobody can actually perform an infinite division, nobody would be able to prove if the remainder goes to an infinitesimal or goes to 0. So it's all absurd. And since the mathematicians wanted to support their theory of real numbers, they decided that the result of infinite divisions would produce the answers that they wanted to get. Another common argument is that if we subtract 0.9 recurring from 1, we get 0. Hence, 0.9 recurring must equal 1. But if 0.9 recurring is not a fixed value, and instead it is a sequence, then in order to subtract it from 1, we need to treat 1 as a sequence and perform arithmetic on sequences or series. 1 can be converted to the series 1 plus endless zeros. Then if we subtract the series from 0.9 recurring, we get a new series as the answer. Or we could treat 1 as a sequence, subtract the sequence for 0.9 recurring, and get a new sequence as the answer. Perhaps the best approach is to work with the nth sum expressions. And when we do the subtraction, we get a result of 0 plus 1 over 10 to the power n. Unlike 1 and 0.9 recurring, this result can't be mapped to base 10 place values. This result might describe a series of journeys in the real world. The first value in the sequence is 0.1, and so the first journey could be to a position at 1/10 of a certain distance. The next value is 0.01, and so the next journey could be to the position corresponding to 1/100th of the total distance, and so on. You'll never get to 0 by following this sequence, and so the result is clearly not 0. Another really popular argument is called the algebraic proof, and it goes like this. Let x equal 0.9 recurring. So 10x is 9.9 recurring. Then we subtract the first line from the second, giving 9x equals 9. And so x must equal 1. This might look very clever, but just think about what's really going on here. We start with x equals 0.9 recurring, then all we do is simply multiply both sides by 10 minus 1 divided by 9, which is the same as multiplying both sides by 1. So we should end up with exactly what we started with. It shouldn't change to x equals 1. If we multiply both sides by 9 over 9, we get 9x over 9 on one side and 8.9 recurring over 9 on the other. And so this time we do end up with exactly what we started with. Now let's consider the difference between the two approaches. It all comes down to what is 0.9 recurring times 10 minus 1. Does it equal 8.9 recurring, or does it equal 9? The question is, can the subtraction operation somehow get rid of the endless terms? If we work with the series instead of the decimal, we write it down again and note the one-to-one correspondence between the terms of the sequence, then we multiply the top line by 10. Note that each term of the series gets multiplied by 10, and we keep the one-to-one correspondence with the original terms. Now we do the subtraction, and the resulting series on the right-hand side is 81 over 10 plus 81 over 100 and so on. It is not the number 9. This would appear to correspond to 8.9 recurring in decimal form. In order to get 9, as in the so-called algebraic proof, we would have to shift the terms, breaking the one-to-one correspondence. And we would have to believe that we can match all of the original terms with all the original terms minus 1. But can we really do this? We could test if this logic is correct if we could find a case where the trailing part cancels out in both scenarios, when we shift the terms and when we don't shift the terms. And this series, 1 plus 1 plus 1 and so on, just happens to fit the bill. On the left-hand side, we won't shift the terms, and on the right-hand side we will. We'll shift by one place, as in the proof. We'll do the subtractions, and we end up with 0 equals 1, which is a clear contradiction. And so this appears to indicate that we can't match the original terms with one less than the original terms. In which case, the algebraic proof is flawed and it doesn't prove that 0.9 recurring equals 1. Yet again, the mathematicians will claim that we're not following their rules. But we used the series 1 plus 1 plus 1, etc. to test the logic of matching all the original terms with one less than all the original terms in a subtraction. The only thing that's relevant to the cancelling out is that the series is endless. But the mathematicians will claim that we can't test the logic with a divergent series. It seems like they are still just choosing to rule out any logic that highlights a problem with their precious real numbers. All of these series are simple geometric series, and so all of them have the same structure in that they just have different first terms and common ratios. And so we stand by our argument that the shift and subtract logic is completely invalid. In fact, it could be argued that every convergent series contains a divergent series hidden within it. If we allow regrouping of the terms, then even a converging series like 0.3 recurring can be easily converted into 3 series, such as 1 plus 1 plus 1 and so on, minus 1 minus 1 minus 1 and so on, and the original series. Then we can line up the terms at different offsets, making the whole thing tend towards different values, such as 1 1/3, or 2 1/3, and so on. If sequences and series have real-world meanings, then this would come as no surprise, because obviously any rearrangement of terms will change the real-world meaning of a series or sequence. The mathematicians will say that 3/10 plus 3/100 and so on is an absolutely convergent series, and we would only be able to make it converge to different values if it were conditionally convergent, because then the Riemann rearrangement theorem would apply. They are effectively saying that it's fine to rearrange terms as long as it can't be viewed as changing the series from one of their categorizations to another one of their made-up categorizations. In fact, rearrangement can even make a series diverge. So surely we can't claim that the different series are fundamentally different kinds of objects just by placing them into different classifications, especially when it's so easy to drift across these made-up classifications by simply rearranging the terms. If we have any doubts about 0.3 recurring being equal to 1/3, then we might be convinced by the argument that 1/3 can be represented as a finite decimal in some bases. For example, 1/3 is 0.1 in base 3. And if a third can be represented in one base, then surely we must be able to represent it in any base. And the only representation that it can be in base 10 is 0.3 recurring. But before the introduction of unending decimals in 1594, it was accepted that values like 1/3 could be expressed in some bases but not in others. 1 divided by 3 can be expressed as 0.333 to n decimal places plus a rational remainder. We can't do infinitely many stages of a division process or even a base conversion process, but mathematicians believe we can theorize about what the result of such an infinite process might be. As already discussed, mathematicians can speculate about what happens to the remainder part, and they can choose whatever answer matches what they want to believe. So the supporters of real numbers choose to believe that the remainder goes to 0 and that the so-called real number, 0.3 recurring, has to equal 1/3. But if we don't accept that endless decimals are the same as constant values, then there is no reason to believe that all numbers must exist in all bases. Next, we have the often overlooked issue about notation, representation, and actual numbers themselves. If we are writing numbers down using the same system of notation based on power of 10 place values, then surely for two numbers to be the same, they should contain exactly the same digits in exactly the same places. But we're told to not be concerned that 0.9 recurring and 1 contain completely different digits in every significant decimal place, because these symbols are just representations of exactly the same number. They are not the number itself. So what does this mean? Well, we are told we should not expect a number system to be unique. For example, a half and 2/4 are two different representations for the same rational number. But if 2/4 isn't the number and a half isn't the number, then what is the number? If we think about what a number is on a computer, then surely the binary bits that represent the number are the number itself. An irrational might be stored as two integers, one for the numerator and one for the denominator. And yes, we can convert one rational representation to a different rational representation, but if these are not numbers themselves, then what are numbers themselves? And since we can't actually store infinitely many digits on a computer, is it really valid to presume that infinitely many digits can somehow exist? Perhaps we should find out if we could actually locate these mysterious numbers wherever they are. Some people confidently think that they've resolved the issue by saying that numbers are just concepts. But what exactly are concepts? Say we imagine two cats on the moon, then surely the number 2 is just a data item in the brain that forms part of the description of what we've just imagined. And so if numbers are concepts, then surely they are just data items in brains. And if numbers on computers are just representations of numbers and not the numbers themselves, then the same can be said for brain data items. And so we still don't know what an actual number is. A mathematician might use the axiomatic system, known as ZFC, to claim that the number represented by a half and its equivalent representations are the ratio of the cardinalities of the sets that correspond to the natural numbers 1 and 2. So now we need to understand what a ratio is, what a set is, as well as what it means to construct things from sets, together with everything that accompanies these concepts. And with all these new concepts, are they representations of things, or are they the things themselves? To say that they are all just concepts doesn't really shed any light on the matter. Let's start by trying to understand what a ratio is using a very simple real-world example. For any given classroom, should it always be possible to state the ratio of pens to pencils in the classroom? Already we hit multiple issues. If the first quantity is 0, then we haven't got a proper ratio, because 0 to a non-zero value is conceptually the same as 0 to any non-zero value. And if 0 is the second number, then the ratio is apparently not well defined because of the implied divide by 0 problem. A simple solution would be to define that any ratio containing a 0 refers to exact quantities, whereas other ratios refer to relative sizes. But mathematicians won't do this because they want two-number ratios to be conceptually equivalent to fractions, and what they want, they get. This raises an important fundamental question. Should reality dictate mathematics, or do we discover abstract mathematics not connected to reality and then retrofit it to the real world? If mathematics was akin to a programming language for modelling physical activities, then we would construct it to correctly describe physical scenarios. And if we encounter a divide by 0, then it would mean we've made a mistake in our modelling. But instead, we try to retrofit abstract mathematical concepts which unsurprisingly result in problems. And we've got all these problems before we've even started to try to get a clear understanding of sets. But the mathematicians will dismiss all these arguments, and they might even call us crackpots for even suggesting that there's a problem. So in order to try to understand what a number itself actually is, we have gone down a rabbit hole, where apparently everything is built up from sets. So now we need to know exactly what a set is, rather than what represents a set. And how did they describe the number represented by a half before set theory was invented? We might suspect that numbers were meant to represent physical quantities in those days, and so half of a standard cake and 3/4 of a standard cake could be said to be equal based on the quantity of cake they contain. But we'll be told that people were mistaken about lots of things in the past, and now we need to go away and study set theory until we see the light. The unsuspecting layperson can feel bamboozled by the many complicated sounding proofs, of which there are many, and all of which supposedly provide undeniable proof that 0.9 recurring equals 1, such as proofs based on Dedekind cuts and the equivalence of Cauchy sequences, not to mention the proof using the nested intervals theorem. The proofs keep coming like paper churning out of a photocopier. Now, if we've already rejected the concept of real numbers, then we're not going to accept these extra proofs which are based on methods for supposedly constructing real numbers. And it turns out that the Dedekind cut approach is effectively the same argument as the formal proof we saw earlier, except that where we used x, we now use a rational a over b. And the Cauchy sequences approach is to define two sequences to be equal if their difference tends towards 0. In this approach, series of endless non-zero terms are simply defined to be equal to a constant. And so there are no significant new arguments here at all. They are just repackaging copies of arguments that we've already covered. Similarly, the nested intervals theorem argument is just a restating of the cat and mouse argument that we discussed earlier. It starts with the invalid assumption that 0.9 recurring is a constant. Then it is claimed that this constant will be between any or all the nth sums and 1, except that the distance from each nth sum to 1 is expressed as a range of values called an interval. Some strange concepts here make this sound like a completely different argument. The theorem states that an arbitrarily small interval will contain exactly one real number. But what does arbitrarily small even mean? To a disbeliever it sounds absurd. And the idea that somewhere at the tail end of an infinite sequence there will be an interval containing one real number sounds like a very slippery way of saying that an infinite sequence will have a last interval without actually calling it that. And since the reality is that this is just a rewording of the cat and mouse argument discussed earlier, there is an equal and opposite argument that indicates 0.9 recurring cannot be a constant. Also, if there is no last interval, then clearly no range can exist containing just 0.9 recurring and 1. But if we go along with the mathematicians' approach to logical reasoning, then we can simply ignore any argument that we don't like. And astonishingly, our axioms don't even need to be valid. In our everyday real-world deductive reasoning, known in philosophy as logically sound, a conclusion is only true if the premises are true. But mathematicians use an approach that is rather dubiously called logically valid, whereby premises are merely assumed to be true, and then conclusions are drawn from them. It doesn't matter if a premise is later found to be invalid, because the conclusion would still be true if the premise had been valid in the first place. And that's apparently all that matters for something to be called logically valid. So we could have the premise that a man can fly all by himself, and my chair is a man. And we can conclude from this that my chair can fly all by itself. This example shows how absurd it is to claim that a conclusion must be true even when the premises don't need to be true. If axiomatic systems are nothing to do with physical reality, then they are no better than fairy tales. So if we make up a fairy tale in which we define that chairs can fly, and where we think that our fairy tale is totally consistent, then is it scientifically correct to say that we have a valid proof that all chairs can fly by themselves? And this matters because maths is supposed to be a science. It's not supposed to be a belief system like a religion. As a science, shouldn't it be based on real-world empirical evidence? The 0.9 recurring debate highlights the non-scientific approach of modern mathematics. Any beliefs not based on things in the natural world are by definition supernatural beliefs. And supernatural beliefs, like ghosts exist, can be disputed and debated on the basis of real-world evidence. Similarly, if numbers are in-brain data items, just like numbers physically exist inside computers, then on the basis of real-world evidence, we could dispute the claim that infinitely many numbers can be said to exist. So the 0.9 recurring problem highlights very serious issues about the underlying nature of mathematics itself. And if it should be an evidence-based subject, that is, if we are classifying it as a science, then the whole of mathematics is currently fundamentally flawed. We've covered a lot of different opinions relating to the 0.9 recurring issue. As we've seen, some of us, like me, expect our arguments to have a basis in physical reality, whereas most mathematicians readily accept as valid any made-up axioms in a so-called abstract axiomatic system. Some of us might think it's absurd to sidestep contradictions by inventing new categories and creating new rules. But the mathematicians might claim that they are discovering these categories and these rules. We might believe we can't choose to accept one argument and reject another when both arguments use the same logic just switched around. But mathematicians think we can. We might relate unending series to things in the real world, like looping instructions, and we might think this shows that they don't need to be mysteriously abstract objects that are somehow not finite. But mathematicians believe that infinitely many non-zero terms can equate to a thing that has no physical manifestation that they call a real number. We might contest that anyone can truly imagine infinitely small points on infinitely thin lines, but the mathematicians truly believe they can, and only an inferior mind would think that we can't do this. These disagreements spill over into disputes about the foundational principles behind all mathematics. The two sides are fundamentally opposed on almost everything, because what makes perfectly good sense to one person will sound like complete and utter nonsense to another. Let's go through some of these differences of opinion, starting with whether or not mystery is a good thing. Huge amounts of abstract mathematics have been produced, and at the time of its production, it's a complete mystery whether or not it will turn out to be useful. And then it is heralded as a major success when a small fraction of the huge body of work turns out to be of some use. Indeed, some of the world's greatest minds might spend their entire professional lives working on things that might never turn out to be of any use in the real world. They often cite complex numbers as a good example of an abstract mathematical concept that mysteriously turned out to have uses in the real world. And they believe that this mysterious usefulness more than justifies the whole abstract axiomatic approach to mathematics. But some of us find it shocking that anyone would defend such a haphazard and chaotic relationship between mathematics and physical reality. Why wouldn't anyone want to fully understand how mathematical concepts like complex numbers relate to the real world? If we did understand this, then we could use this better understanding to actively identify the real-world scenarios that would benefit from the application of such concepts. To some of us, the argument, abstract stuff can prove useful, is of the same form and has the same amount of credibility as the claim that the expression God moves in mysterious ways can provide justification for religious belief. If mathematics is a science, then it should be based on physical empirical evidence and not a belief that we can imagine things that are mysteriously non-physical. It is even claimed that mathematics is superior to the sciences, because whereas a scientific theory might later be proved wrong, this can't happen in mathematics. The reason mathematical proofs can't later be proven wrong is precisely because they don't rely on physical reality. They are underpinned by abstract concepts that have supposedly been rigorously defined. But some of us find it bizarre that anything can be claimed to be true forever. Such a claim can only be made using so-called logic that can't be substantiated by physical evidence. If an underlying definition or assumption is shown to be wrong, then we would expect any proof that uses them to be reassessed or reworked, because that also might be wrong. This forever true stance is yet another assertion that makes mathematics sound more like a dictatorial religion than a science-based discipline. Another argument is that usefulness is far more important than correctness. The current approach to mathematics has been stupendously successful in underpinning the sciences, and this apparent success means that the abstract approach must be far superior to any other approach, such as one that tries to reflect observations in physical reality. But we haven't developed a physics-based approach to mathematics, and so we can't assume that the incumbent abstract approach would necessarily be the best. When a car accelerates, it might do this via a finite series of discrete velocities, as opposed to being truly continuous. In which case, any model based on continuous motion that is supposedly infinitely divisible would be inherently flawed. And so the apparent success of the abstract approach could just be down to the granularity of the real world being at such a small scale. Religious scriptures can be useful, such as to provide moral guidelines, but this does not mean that they contain superior logic over atheism. A similar argument is that most mathematicians agree on what they consider to be correct logic. And they agree that axioms don't need to relate to reality. And as already mentioned, it is stupendously successful. And so for all these reasons, it must be right. But for well over 1,000 years, almost all people thought that Aristotle's theory of free fall was correct. And there are many countries in the world today where most people appear to believe that the scriptures of certain religions are correct and accurate in the real world. And so yes, a consensus of opinion might be very persuasive, but it doesn't constitute proper scientific evidence of correctness, and that's what really matters. It's one thing to say that infinitely thin lines, or infinite collections of numbers, or perfect shapes are concepts, but shouldn't we then try to understand exactly what a concept is? Mathematicians claim that we can talk about perfect things. They might even claim that a perfect continuous straight line need not be represented by an imagined picture of a line. It can be defined by an equation. But we might think that it's obvious that an equation is something that can be used to try to construct a line. It is not a line itself. But mathematicians never doubt their ability to imagine non-physical perfect forms. But as disbelievers, we might question the ability to imagine such things. For example, if we try to imagine a perfect cube, then we probably create an imperfect picture of a cube in our minds, and we pretend that its edges are continuous and infinitely divisible. Shouldn't we try to understand what a concept really might be, possibly by considering how we might program a computer or a computer brain to conceive of something such as a natural number, or even a real number? Some mathematicians will say that, since we are cranks, our views should be banned. We clearly don't understand what we are talking about. We spread misinformation, and we claim that there are inconsistencies when there clearly aren't any. But we believe that all sides of an argument should be allowed to be heard and properly debated, rather than one side silencing all opposing voices through bans and censorship. It doesn't really matter if a mathematician identifies themselves as a Platonist or as a formalist, because as long as mathematics appears to work, then nobody cares a hoot about the philosophy of its foundations. But we might object to the claim that mathematics is not based on anything physical. And even though it might be true that most people don't care about mathematics' foundations, perhaps they should. Perhaps the world would become a better place if all the people in the world could agree on what the best approach to logical reasoning and logical deduction should be. But they, the mathematicians, think it's logically correct to define things into existence. And apparently we never properly understand the meaning of supposedly simple statements like 1 + 1 = 2 without first understanding higher level mathematics such as ZFC set theory. And if you don't come armed with a contradiction in ZFC, then you'll be told to go away and educate yourself. But mathematics has been around long before the invention of ZFC set theory, and so how can that be so fundamental? Say we were to try to reinvent mathematics, starting with, for example, just unsigned whole numbers, addition, and the equals sign, all of which are constructed as and when required, as would take place in a computer. Then would we really need to define our numbers in terms of infinite sets? Why can't we define them as descriptive terms that can relate to physical objects or lengths? Why should we need to define them as non-physical things and claim that all of them can mysteriously already exist somehow? So, in order to accept that 0.9 recurring equals 1, we have to accept that infinitely many terms is not an absurdity, and that they can all sum to a constant value, and that it's fine to reject any logic that would prove us wrong, even if we've used the same kind of logic, and that we can avoid contradictions by reference to categories and rules that we can claim were discovered as opposed to being made up to suit our arguments. If we don't agree with all of this, then the only credible position is that 0.9 recurring cannot equal 1. The lack of logic based on evidence means that the validity of any piece of mathematics becomes a popularity contest. A prime example is Cantor's theory of infinite or transfinite numbers, which was initially widely and fiercely rejected. A current example concerns the remaining unsolved Millennium Prize problems, each of which is worth a prize of $1 million to anyone with a valid solution. The problem is that one group of mathematicians might think a solution is valid, whereas another group might not. And so the rules have now changed to be based on general acceptance by the mathematical community, regardless of whether or not the proposed solution is actually valid or invalid, whatever that might mean in an abstract mathematical world. Now that we are nearing the end of the video, I hope you will go on to discuss the issues raised on other forums, so that we can all help to raise the awareness of these important foundational problems. Yes, we'll face a lot of abuse from the moronic haters out there, but we can rise above their level and just ignore the insults and name-calling. If we're not alone in the universe, then perhaps we should focus on preventing the possibility of Earth's approach to mathematics becoming the laughingstock of the universe. Finally, if you found this video interesting, then please click like, and if possible, share a link to this video on social media in order to increase awareness and promote further discussion. It would also be great if you could subscribe to my channel. Thank you for taking the time to watch, and I hope you enjoy my other videos.